Our speaker today is Karl Kreutz. Karl got his Bachelor of Arts in Geological Sciences from the State University of New York at Buffalo. He got a master's degree from the University of Maine, and then his doctorate in Earth Sciences from the University of New Hampshire. He was a postdoctoral scholar at Woods Hole Oceanographic Institution, and ever since then, he's been at the University of Maine, where he started out an assistant professor and is now a full professor in the Climate Change Institute and School of Earth and Climate Sciences, and he's also director of the Stable Isotope Laboratory. And Karl is actually one of our candidates for the Evans Family Chair here at the Engineering School. So with that, I'll hand it over to Karl to talk. Thank you.
Is my microphone on? Sounds like it is. Thank you, Ian. And thank you to Thayer School, of course, for inviting me to come talk. It's been a very interesting and active morning already, so I look forward to now sharing with you some of our results from work we've been doing in the Arctic for, well, the better part of 20 years now. And what I want to present to you today is specifically related to our interest in looking at the water cycle, how it's changing in the Arctic now, how it may change in the future, but specifically how the records that we develop from ice cores recovered throughout the Arctic give us some perspective on what we might expect in a warming climate and the response of the water cycle to that warming. So I just wanted to point out quickly that I'm going to have a few, what I think are really nice pieces of artwork throughout my talk. They're all produced by a former graduate student of ours, Jill Pelto. So this one is her artistic depiction of the decrease in Arctic glacier mass balance over the past several decades. So just wanted to acknowledge Jill because she was very kind to let me use her, some of her pieces. So I like this image of the Arctic from NASA for lots of different reasons. One is because it's just beautiful to look at, but it also depicts well the various aspects of the cryosphere that many of us are interested in. So the large, of course, ice sheet of Greenland, the ice caps in the Canadian archipelago islands, the large amount of ice that stretches from Alaska down into the Yukon and British Columbia. Of course, we've got the Arctic ice cap and the sea ice up here, and then a more transient feature on the landscape, some snowfall. I think this image was taken perhaps in March or April of, I forget which year this is, but this sort of gives us a nice overview of the different cryospheric components in the Arctic. Whoops. Now, of course, we're probably all aware that the Arctic is warming quite rapidly right now. These are just two different looks at it. The one on the top is taking the snapshot from 1960 to 2013, and you could already see in that time period the higher rate of warming in the Arctic with respect to lower latitudes. But certainly if you take a more recent time period, so here 1990 to 2013, that Arctic amplification of temperature is becoming quite apparent. So the rate of temperature rise in the Arctic over this time period is at least twice of that in the lower latitudes. Another interesting feature here is if you look at the temperature data in time series for both the lower latitudes and then the Arctic in red, you see that since the mid-1970s, that's where the temperature trends really start to diverge. So the Arctic really starts warming at a faster rate than the lower latitudes beginning here in the 1970s. So that's a time period I'm going to come back to a little bit later in my talk. Oh, I guess I can do it from here. There. So one of the questions we're interested in addition to the change in glacier mass balance, is what effect is this warming going to have on overall Arctic hydrology? So in addition to just, again, changes in glacier mass balance and runoff, if we think about the Arctic hydrological system in broader terms, one thing that is likely going to be happening is that moisture, there's going to be increase in moisture flux from lower latitudes into the Arctic through the atmosphere, and also the well-documented decrease in sea ice extent is, of course, exposing more of the ocean, and that tends to promote an increase in evaporation of ocean water into the local Arctic atmosphere. Now we have tools for getting at some of these things. Some involve looking at the isotopic composition of the water itself, so the stable isotope ratios of oxygen and hydrogen in the water itself, and there's been a lot of active research here at Dartmouth looking at fingerprinting this moisture coming up off of evaporating water from the Arctic Ocean as sea ice retreats. So it's those kind of tools that we can bring to bear on this issue of trying to look at the interplay of these different processes. So if you look at models that have investigated this problem out into the future, this is a compilation of 30 different general circulation models that are in the Climate Model Intercomparison Project. And they've been run out to 2100 and looked at the precipitation increase that would occur in the Arctic out to that time period. And so these models have been run with the high carbon emission scenario, RCP 8.5, you see that all the models are consistent in saying that there is going to be a fairly large increase in overall precipitation in the Arctic through this century. The contribution is going to be, again, both from the transport of moisture into the Arctic from lower latitudes and also a contribution from evaporation due to sea ice retreat. So if you look across all the models, they disagree somewhat on the relative contribution of those different sources, but all of them have those two sources involved, and the increase occurs regardless of which emission scenario. Of course, it's a bigger increase with the larger carbon emission scenario, but both scenarios show a fairly large increase in precipitation. There's also a big seasonality component to this. So this is the same compilation of models now. And if you look at the precipitation increase across the seasons, we see that the largest increase, at least according to this model suite, is going to occur in the wintertime, which makes some sense as we lose sea ice in the late summer and early fall. Then we have an increased proportion of the contribution from evaporation. So there's this large seasonality increase. Another issue that the Arctic is likely going to face is what proportion of this precipitation is falling as snow and what proportion is falling as rain. So right now, throughout the Arctic, most precip falls as snow, but the models predict that's likely going to change into the future, and the Arctic is going to see quite a bit more rain. So all of those combined are going to have effects not only on the overall hydrologic cycle, but certainly on ecosystems, runoff, and other impacts as well. So to summarize, we know that the Arctic water cycle is undergoing quite a bit of change right now. We see that in the sea ice loss that's ongoing, the decreases in glacier mass balance that have been widely documented. Again, if you look at the model suites I just showed you or others, they are remarkably consistent in projecting a strong increase in Arctic precipitation in the coming century. And it's the combination of both mechanisms that are going to contribute to that. Seasonality is going to be important, and as is the balance between rain and snow. We only have really two periods of warming to study this issue. Of course, one is the recent warming that I showed you from the 1970s on. The Arctic did go through a fairly rapid warming in the early 20th century, so that provides us another test case to look at. But really, those are the only two periods of warming in the Arctic that have been captured by the instrumental record. So the questions we're asking are, what can we learn about the Arctic system response to a warming climate from the record that's stored in ice in the Arctic? And of course, what happens to the water cycle during periods of both abrupt warming, so when we've got a rapid increase in temperature, but also periods of sustained warming. And when I say sustained, I'm talking, let's say, over centuries to millennium. What happens when you have a warming sustained over that time period? What happens to the water cycle? What happens to ice extent? So we're going to look to the ice archive to try to get at some of these questions. So I'm going to start with, where I got started in all of this, and that was in an ice core that was recovered in the summit region of Greenland in the late 1980s and early 1990s. It was called the Greenland Ice Sheet Project 2. It was an ice core that was drilled from the surface of the ice sheet to the bed, which was a little bit over 3,000 meters of ice recovered at GISP 2. And this is I think, what I would consider one of the most iconic records from that ice core. This is, again, the stable isotope ratio of 018 to 016 in the ice, starting with today here on the right-hand side and going back 60,000 years on the left-hand side. And what we can see is that the water cycle, temperature variability, this 018, 016 proxy is generally taken as a proxy for temperature, but there's also a component of hydrology involved in this as well. But in general, the thing that jumps out at us is this huge variability in the system particularly during the last ice age. So each of these rapid warmings has been given a name. They're called Dansgaard-Oeschger cycles, named for the two scientists who originally described them in Greenland ice cores. There's many of those Dansgaard-Oeschger cycles through the last ice age. So we come into the most recent, one of the most recent rapid warmings, the Bowling-Allerod transition. We go back into the Younger Dryas period, and then we rapidly warmed from there into the last 10,000 years, which is known as the Holocene period. So we can learn something, hopefully, by studying these rapid climate transitions and trying to figure out how the Arctic system plays into a more global picture. That was where I started working on this. One of the first papers I published was trying to look at comparing what was happening in the North Atlantic, specifically the Greenland Ice Sheet Project 2 core, to what was happening in Antarctica. And these figures from almost 20 years ago look somewhat antiquated now, but they still do the job. We see that over the last 1,000 years, so today, or modern times on the left-hand side now, and about 800 years ago on the right-hand side, there was a transition around the year 1400. This is in a parameter known as the sodium concentration that we measure in the core, and we generally take that as a means for reconstructing the atmospheric dynamics in the region. So we noted that there was an essentially synchronous change in the sodium deposition, hence the climate dynamics in these two regions, right around the beginning of, this is known as the Little Ice Age. So this was intriguing. Since then, in the past 20 years, we've come a long way in our interpretation of the Arctic, Greenland, and the North Atlantic in a more global context. These are some results now from a suite of ice cores, deep ice cores that have been recovered from Antarctica over the past 20 years, where we now have very precise chronological control. So these records from Antarctica have been matched in time very closely with the Greenland ice core records, primarily through matching very high resolution measurements of methane in the core, so a globally well-mixed greenhouse gas that can be used as a time marker in all these cores. And what we've seen is that if you composite all the different warmings that have occurred during the last ice age, every time Greenland warms rapidly, there's a nearly synchronous response in the isotope record in all these Antarctic cores. And this is an isotope parameter known as the deuterium excess, which is a derived parameter based on both the hydrogen and the oxygen isotopes in the ice. And so it's generally taken as a proxy record for the moisture source region. So where's the moisture coming from that's getting down to Antarctica? So the interpretation of this is as Greenland warms, there's a synchronous change in the moisture source, where this moisture is coming from, and we think that's driven by changes in the westerly wind system in the high latitude southern hemisphere. So this is work that's been done by grad students and postdocs, Brad Markle and Christo Boisart. But what it really points to is the connections that are inherent between the Arctic and the Antarctic. we've got a lot of work yet to do on this, but one thing has been clear, and that's certainly from this core here in what we call Waste Divide, so West Antarctica. There's definitely a connection between the Pacific sector of the southern hemisphere and what we see going on in the North Atlantic. So now I want to take you to show you some more work in our focus on the Pacific sector, particularly now in the Pacific and its role in Arctic climate. So this is a site that we've been working at for the better part of probably at least 10 years now. This is the Mount Hunter ice plateau, which is in the middle of Denali National Park. Denali, the peak of Denali actually sits back over here. You can't see it. So this is a beautiful ice plateau sitting at about 3,900 meters elevation. It's a small camp that we had there when we were drilling ice cores several years ago. This is what our camp looked like, all powered by solar and wind energy. The drilling we did that season, we recovered 2 ice cores from the surface all the way down to the bed, which were both about 210 meters long. Here's a picture of some of the ice that was recovered right down near the bed, so you can see the silt that's present in the ice. We have spent a lot of time prior to the drilling collecting a lot of different geophysical data, mostly in the form of ground-penetrating radar, to really get a sense of the stratigraphy of the glacier, the flow dynamics of the glacier, so we could put that all together into a 3-dimensional flow model to really understand primarily the vertical velocity and the vertical thinning of the ice. Because for paleoclimate studies, the first thing you have to do is put an age on the ice, and the better you know the age at any depth, the better your paleoclimate reconstruction is going to be. So this is the existing depth versus age chronology for the Denali cores. It goes back now to about 810 AD, so roughly 1,200 years at a very high, so annual resolution, but at a resolution that's sufficient to allow us to interpret seasonal changes in many of the parameters that we're interested in. So these are 2 of the records that have been published from the core so far. Both of these published in collaboration with the Dartmouth group here, but the lead author being Dom Winsky in 2017 and 2018. The top panel is the snow accumulation rate at the site. So one thing that jumps out immediately to us is that and again, here's today on the left-hand side, on the right-hand side, and 1,200 years ago on the left-hand side, is that there's been a dramatic increase in the snow accumulation rate at the site over this time period. The increase looks like it begins around 1850 and continues to today, and that's well outside the range of variability we've seen over the past millennium. Again, because these records are so high resolution, you can actually separate out the winter snowfall, which is in blue, from the summer snowfall in red. So we see that over the past 150 years, winter snowfall has always dominated at the site, and most of the increase in overall accumulation has actually been driven by the increase in winter accumulation. The second story that's really emerged from these cores so far is the change in the frequency of melt at the site. So again, the site sits at 3,900 meters elevation, so there's not a lot of melting that occurs at this site, but there is some that occurs in the summertime. And what Dom noticed is that there's no melt features present. This is all done by optically imaging the core. There's no melt in the core until we come into the mid-1800s, and then both the thickness of the melt layers and also the intensity of the melt, so how much melting occurred in a particular layer, both of those increase dramatically as we come into the present. So these 2 things together give us a pretty solid understanding of both the moisture dynamics at the site and the the advection of heat and the temperature change at this site over the past millennium. All of that has been well verified by comparing those records to modern observations. So on the top here is the correlation between the accumulation rate record and sea level pressure variability in the region. And so we see a strong correlation. When sea level pressures are low in the North Pacific, that tends to advect more moisture up into the Mount Hunter region, so giving us a strong negative correlation. This is the same regression based on instrumental data. So there's a strong correlation between what's known as the Pacific North American Index and sea level pressure. The accumulation rate record is also well correlated with what exists for station precipitation data in the region. So we feel, and Dom, of course, published this in this paper, that there is a strong connection between the precipitation at the site, also the temperature at the site, and what's happening with the broader climate dynamics of the Pacific. If you take the accumulation rate record and look at it in a longer context, particularly with respect to how the accumulation rate compares to what's happening in the tropical Pacific, proxy records in the tropical Pacific also show a warming beginning around 1850. So there's a consistent story has emerged from this. When the tropical Pacific warms, that tends to drive changes, dynamical changes in sea level pressure in the North Pacific. That then tends to advect more moisture and heat, at least into this part of Alaska. So all of this, these different pieces tend to hang together in a fairly coherent way. We're now working on interpreting the stable isotope data from these same cores. So again, the same time period here. Today is on the right-hand side, 800 AD over on the left-hand side. Again, the data here is available at very high resolution, so we can really probe changes in the isotope record and its relation to climate dynamics on a seasonal basis. The 018-016 ratio is here on top. There's no obvious long-term trend in the data. So a working hypothesis at this point is that change in the proportion of winter precipitation versus summer precipitation is probably playing a role here, winter precipitation being more isotopically depleted than summer precipitation, so any temperature-based trend that we might expect to see here may be offset by that change in the precipitation seasonality. On the bottom is the deuterium excess record, so the same measure that I showed you from the cores down in West Antarctica. Here there is more of an obvious trend coming out of the beginning part of the last millennium into what we would classically consider the Little Ice Age, and then some trend beginning around 1850 coming into present. So again, a working hypothesis at this point, given that deuterium excess is typically interpreted in terms of the moisture source area from which the moisture comes from, is that we may be seeing a shift from a more southerly moisture source to a more northerly moisture source, again, as the tropical Pacific warms, the Aleutian low deepens, and we get dynamical changes in the North Pacific. But that's, we're still actively working on this isotope record, so more to come on that. All of these interpretations are seem to be very consistent with a number of recent publications that have been looking at the connection between the Pacific and not only the recent warming of the Arctic, but the warming that occurred in the Arctic in the early 20th century, and the contribution of Pacific Ocean variability to the loss of sea ice in the Arctic Ocean. So essentially, it's if you look at the observational data, it's a story consistent with what I just told you from the paleo, the ice core data, in that when you warm the tropical Pacific, that tends to drive lower sea level pressures in the North Pacific, driving heat and moisture up into the Arctic. And it's worth noting that this pattern, which is known as the warm phase of the Pacific decadal oscillation, the Pacific shifted into this warm phase in the mid-1970s, and has been roughly persistent since then. So when I showed you the the temperature trends in the second graph I showed, that increase in divergence of Arctic temperatures since the mid-1970s is now thought to be, at least in part, driven by this persistent change in the tropical Pacific. So there's a lot of work, a lot of active work in the observational community being done on this. And again, we're trying to provide additional information, additional perspective on it from a paleo ice core perspective. Okay, so that's some context for recent Arctic warming. What about other known times of more persistent warming in the Arctic? So this is a figure from a global compilation of temperature proxy records from Sean Marcotte and colleagues from 2013 over the entire Holocene. So again, today over on the right-hand side, roughly 10,000 years on the left-hand side. And in this global compilation, you see that the early part of the Holocene was generally warmer. These are in temperature anomalies by about 0.4 degrees relative to a recent period. So this period between 10,000 and 6,000, roughly speaking, is known as the Holocene Thermal Maximum. And this is a signal, again, that is seen globally, certainly not one that is, we have to take this figure with a bit of grain of salt. It's not that well characterized in all regions. There's quite a bit of spatial and temporal variability in this Holocene thermal maximum, but in general, it is generally seen as a sustained period of warmth, particularly in the Arctic. There's many Arctic records which show elevated temperatures in the early Holocene. So it's a time period that we would like to investigate, again, asking the question, during the sustained period of warmth, what was the hydrological response in the Arctic? So these are some new results, again, from the ice cores recovered on the Mount Hunter Plateau. So the axis here is depth, so surface down to the bed at the bottom. Now it's in meters water equivalent, so a little bit less than the absolute depth of 210 meters. These are, what I'm showing you here are radiocarbon dates. We've done this in collaboration with our colleagues in Switzerland at the Paul Scherrer Institute. I just came back from there last week with some of these new data. They have a system that is capable of doing radiocarbon measurement on basically water-insoluble organic carbon that's in the ice. And we're talking about doing measurements on roughly 5 to 10 micrograms of carbon per sample to get a radiocarbon date. So it's an amazing system they have. It's the only one that I know of in the world that's capable of doing this. So what I'm showing here are the chronological information that exists from the Denali core. So in black is the annual layer-counted depth age scale. In the green is just a pretty simple two-parameter model fit, assuming a constant accumulation at the site and a simple assumption of vertical thinning. In the red are the radiocarbon dates that we've done so far. So a few things to note here. One is that the dating actually worked. So this was, as far as we were concerned, very exploratory work. We were really not sure that we were going to be able to get enough carbon out of these samples to do the analyses, but we were quite pleased to see that we seem to have gotten reliable data. The second thing is that the dates, the age information is in chronological order, so it doesn't appear that there's any major stratigraphic disturbances in the bottom ice of the core, which, again, we weren't sure that was going to be the case, so we're glad to see that there is what seems to be stratigraphic continuity there. The third thing is that the oldest date down here is about 9.5 thousand years ago. So it certainly appears that the ice here at Mount Hunter survived the Holocene thermal maximum. So that period of sustained warmth, which again has been magnified in the Arctic, ice here, at least at this elevation, did survive that period of sustained warmth. And then lastly, again, this fit assumes a constant accumulation rate at the site. These two data points up here, fall within error of the fit, so we aren't going to make too much of those, but this data point right here actually does fall off the fit by about a couple thousand years. It could be an anomalous data point. Of course, we are going to go back with more samples above and below and at the same level to confirm that date, but if it turns out to be accurate, then it does require some change in the accumulation rate at the site during the Holocene Thermal Maximum. So it's possible we're seeing some hydrological response to the warming of the Holocene Thermal Maximum at this site. We'll see how that goes when we get more data, but it's an intriguing idea to track down. So the Holocene Thermal Maximum, as I said, there are other data from different parts of the Arctic. The red curve on the top here, again today on the right-hand side, 11,000 years ago on the left, comes from an ice core from our Canadian colleagues at the Agassiz ice cap. And this, again, this is a record of summer temperature at the Agassiz site based on melt layer stratigraphy. So the same type of work that we did in the Denali ice core, identifying melt features with optical logging. Our Canadian colleagues have done the same analyses in the Agassiz record. And certainly the rate of melting during the Holocene Thermal Maximum shows a rise of summer temperature on the order of several degrees Celsius. These are the stable isotope records, both from the Agassiz record and the Rhineland ice cap, which is over here. Both of these records have been corrected for changes in elevation that occurred on those ice caps through time, which does have an impact on the stable isotope signal. So these are elevation-corrected records. And you do see a spatial difference between the two isotope records. So it's known that the Holocene Thermal Maximum in this part of the world is probably was not a spatially coherent signal, but has regional variability, again, shown between comparison of Agassiz and Rhineland. But what's even more intriguing is if you compare particularly the isotope records from this part of Greenland and the Canadian Arctic to the isotope record that was recovered from an ice core drilled at the summit of Mount Logan, which essentially sits right next to the Pacific Ocean, so is an accurate monitor of Pacific Ocean conditions. The ice core record here at Mount Logan, we are reasonably confident goes back into the last ice age. When I say reasonably confident, I mean that if I had plotted the entire 018 record, it does drop down quite a bit here, suggesting last glacial maximum type isotope values in the lower part of the core. But what I've done here is I've plotted the isotope data from Mount Logan on a scale that's 10 per mil, so that's comparable to, that's the same scale for the Agassiz and Rhineland data. And you can see that at Mount Logan, the isotope variability is much, much higher than what's been observed in the Agassiz and the Rhineland cores. So we don't have a great explanation for that at the moment. It likely has something to do with the Pacific dynamics, climate dynamics that I was talking about in the modern period the more modern period for the Denali, the Mount Hunter records. But we've got a lot of work to do here to interpret that record. We are going to be going back to Mount Logan over the next couple of years and re-drilling this core, because this core was drilled in the early 2000s before we really had developed the geophysical techniques to understand the stratigraphy and ice flow at these sites. So we want to go back and do all that geophysics, re-drill a core, and really confirm these signals and before we get too far with this interpretation. But again, some of these signals, particularly this one around 4,000 years ago, is sufficiently large and seen in enough other paleoclimate records from the Pacific to actually warrant this being used as a stratigraphic tie point for the mid-Holocene as in an official capacity. So That gives us a nice target. We'll redrill the core, see if we can reproduce these signals, and then if true, really try to understand Holocene climate dynamics in this region. Okay, so that's the Holocene Thermal Maximum. What about earlier periods of sustained warmth? And when I say earlier periods, I mean what happened to Arctic ice during previous interglacials. So that occurred roughly every 100,000 years for the past million or so years, and then transitioned into a different regime prior to that. So coming back to the GISS-2 record, where I started, in 1993 when they got down to bedrock, the drill they were using was capable of being swapped out. They put a different drill on, and they were actually able to collect several meters of bedrock at the bottom of the borehole. So the picture on the top is the last few meters of very silty ice that was recovered with the ice core drill at the bottom of the borehole, and then they transitioned into drilling bedrock. And so people have recently, both Paul Bierman and Jörg Schaefer and colleagues have done cosmogenic isotope analysis both on the silt that's in the silty ice at the bottom of the borehole and also in the bedrock that was recovered from the bottom of the borehole. So they're using measurements of cosmogenic beryllium-10 and aluminum-26. These are different techniques. It's meteoric beryllium that's in coming off the silt, and then in situ produced beryllium-10 and aluminum-26 in the bedrock. So the question, particularly with respect to the in situ the in situ measurements on the bedrock, the question being asked is, when did that bedrock last see the sky? So when was the last time the ice was removed such that you could get cosmogenic isotope production in this bedrock when it was exposed? And so this is still an active area of debate, how to interpret these data, but at least according to Jörg Schaefer and his colleagues, the in situ isotope data from the bedrock require at least some period of deglaciation during the past 1.1 million years. There's sort of at least 3 different scenarios that they proposed that could explain the data they have, but I think their favored explanation right now is sort of number 3 here, multiple exposures over the past 1.7 million years. So according to them, at some point in the last 1.7 million years, this bedrock underneath the Greenland ice sheet did see the sky. So we'd like to try something similar, so ask the same question in Arctic glaciers, so not underneath the Greenland ice sheet, but on these Arctic glaciers. When was the last time the bed surface there last saw the sky? So when was the last time the ice was gone? And so we're going to give that a try in the basal ice recovered from Mount Hunter. So again, here's a picture of it. You can see the silt in the ice, and there's also quite a few actually, millimeter-sized pebbles in the ice. So we're going to try the in situ technique for measurement of beryllium-10 and aluminum-26. Again, like the radiocarbon analyses I showed you, this has been funded as an exploratory attempt. We're not really sure that it's going to work, but not really sure we have enough material to make these measurements, but we're going to give it a try and see what happens, because I think the ability to recover not only sediment-rich ice, but also bed material itself and do these type of measurements. Again, Greenland is the only place in the Arctic that I know of that it's been done. I think this approach is really rich for helping us understand past ice response to periods of sustained warmth. In this case, asking the question, what was the last time this ice was no longer there? So with that, I'll summarize. We see today that Arctic hydrology is changing quite rapidly. I think there is a lot of value in studying the ice core record during periods of rapid and also sustained warmth, and trying to figure out what that can teach us about the system response to rapid warming. The Mount Hunter record gives us an example of that. So we see that there were large hydroclimate changes in the North Pacific translating into the Arctic since around 1850. And those are certainly the largest changes in the past millennium. We think now from the radiocarbon dates we have on the bottom of the basal ice from Mount Hunter that ice there did survive the Holocene Thermal Maximum. Of course, one caveat with that is the elevation of that site is 3,900 meters. So all it really tells us is that ice at that elevation survived the Holocene Thermal Maximum. Most of the ice, at least in Alaska, sits at lower elevations. So we still have much to learn about the ice response in the Arctic to the Holocene Thermal Maximum, and we also have a lot to learn about the seasonal characteristics of hydroclimate during the Holocene Thermal Maximum. We are targeting several new sites, ice core sites in the Arctic that we think have the possibility of being able to actually reconstruct hydroclimate on a seasonal basis throughout the Holocene. We've done a lot of work to identify those sites, but I think we've got several really good candidates now, including going back to the GIS-2 site and re-drilling that, drilling a new core at that site back through the Younger Dryas period. So that's on our list of our wish list of things to do. And then lastly, asking the question, when did Arctic alpine ice survive previous interglacials? And I'm thinking primarily here about the Eemian, which was about 130,000 years ago. Did this ice sitting both at elevation, high elevation, and lower elevations, where do we see ice surviving and where do we see ice disappearing during the Eemian? Because that period of sustained warmth may give us some good analog information for where we might be heading in the future. So with that, I'll stop and take questions. Thank you.